-1. Hi, welcome back. Matthew 34. I'm your host, Steve Dugu. Let's do a practice exam because our exam is tomorrow, March 12th. Yeah, I think we've talked about this announcement a couple of times, but there's an announcement on D2L if you want to know more about the exam. Cool. All right, so we're going to work on the practice exam, but Monday's class period also has a copy of the updated formula sheet, as well as I highlighted all of the parts off of the formula sheet that I think you pay the most attention to. Basically, just everything that shows up on this unit, right? So if it's highlighted, I think you should know it. And if it's not highlighted, you probably don't need to worry about it for this exam. Cool. All right, let's go do the practice exam. So make that bigger, and we are going to start with an integration problem. So step number the first, evaluate the line integral. Given that C is the arc of the unit circle, nope, not the unit circle, circle with a radius of 3, but still centered at the origin. And we're going to traverse counterclockwise from 3, 0 to 0, -3. So the first thing I want to know are which two angles that these points correspond to. Right, if I'm going to be traversing along a circle, I'm probably going to go to polar coordinates to describe that shape, which means I would like to know what two angles these are. 3, 0 goes directly to the right along the x-axis. Right, it's 1, 0, but out at a radius of 3. It's about a radius of 1. So that's going to be an angle of 0. So theta is 0 at 3, 0, but at 0, 3, I'm pointed straight down, right? Headed down the y-axis, which is an angle of 3 pi over 2. So in between those 2 points, I'm going counterclockwise, so I'll traverse the circle the usual way, starting from the positive x-axis and going 3/4 the way around the circle. That's the path it's describing for me. And then there's a whole bunch of hints that tell us how to integrate a few trig functions, which might suggest that there's some tricky integration in this problem. If I wanted to parameterize my curve, I could probably say that R of t is 3 cosine t, 3 sine t. 3 sine t, there we go. Right, since I'm headed around a circle, I know my radius is 3. Anytime I'm thinking I've got a circular path, polar coordinates is going to be our best parameterization option. So if we're going around a circle, think about polar coordinates. Ours is the particular case where r is equal to 3. And any good parameterization also needs to include bounds for its parameter. So I need to include some sort of domain for t. Our usual best guess is 0 to 2 pi. Without thinking about it at all, we should always start thinking about 0 to 2 pi and then decide if we need to change that. We already thought about it, though, because we said 0 to 3 pi over 2. From here, if I were going to integrate this thing directly, I would find r prime, plug that in for dr, substitute in x and y based on what I have for r, and then I'd be looking at some sort of an integral that the hints are probably telling me how to solve. But I'm here to argue there's an easier way than all of that. So let's forget about everything we just did and start again. The thing that I'm looking to integrate here is a vector function. Right? We have 2 different types of line integrals that we look at, which for the exam tomorrow, know that there are 2 different types of line integrals. I can either integrate a scalar function, take the line integral of a scalar function. That one's on the formula sheet. That's the integral of f ds and then it shows you how to integrate that. Involves the magnitude of r prime. But there's also a vector function line integral. And this is a vector function, right? Our field f up here, we know what it is. That integrand, or at least the part that's before the dr, is a vector function. So I want to use one of the vector integration techniques for a line integral. And anytime we're integrating a vector field, we might as well check to see if that field is conservative before integrating. Because if it is conservative, I could use the fundamental theorem for line integrals instead of having to compute it directly, because the fundamental theorem is a lot nicer when it works. So I'm going to go do that. I'm going to highlight P and Q being P is this half, Q is this half, right? P and Q are the components of our field F. P is the X component, Q is the Y component, because they just go alphabetically. P and then Q and then R, I think is the order that the alphabet goes in. If we had a third element or a third component, we go to that. Right. All to say, I want to see if this thing is conservative. And the way we do that is we check QX, Q partial X, and we check P partial Y. And our hope is that these two partial derivatives come out equal to each other. You'll notice that we are taking the opposite partial derivatives with the position that P and Q are from, right? P is the I component, or normally the X component, but I'm going to do its Y partial derivative. Similarly, Q is the Y component, but I'm going to take its X partial derivative. And remember that we're doing that because we're assuming that P and Q are already partial derivatives. It's what we want to assume for a conservative. That they're already partial derivatives, then I can integrate them back up to find the original function, or at least find a potential function. So I'm going to do the opposite derivatives here to see if they're equal, because then I'll have done the same two operations, is the idea behind a conservative field. So let's go check that. QX, this thing is 2x partial y. I scrolled it off screen, but it's up there. Right, the yellow one was 2x. But I misspoke at the end there. I want 2x partial x. Right, I'm doing the x partial on the yellow bit. And when I do that, I get 2. Head over to the purple side. P for purple. It was 2x plus 2y. And this time I do want the y partial. If I take a y partial derivative of 2x plus 2y, I get 0 plus 2. So I can see that these two partial derivatives are in fact equal to each other. So I've shown that my field is conservative just by checking these two partial derivatives. So a word to the wise, if you're asked to show that a field is conservative, you should take these two calculations. Right? Take our two partial derivatives and show that they're the same thing. That's the easiest way to show that a field is conservative. It's to take partial derivatives of its components, show they're equal. So if that worked out, that means I should be able to integrate each of these pieces back up. So I want to integrate 2x plus 2y dx and see what I get. I also want to integrate 2x dy and see what I get. So I'm switching the P and Q back to the correct alphabetical order. We follow the yellow and the purple, they swap places, just to keep the X parts and the Y parts in the same position. So don't worry too much about that. But anyway, when I integrate those two things, I get x squared plus 2xy, and I get x squared for my two individual integrals. So if I'm looking for a potential function, right, the potential function being just some scalar function whose gradient is the field I started with, it should be the union of these two things. So it's just going to be x squared plus 2xy. And then again, I should see that if I were to take the gradient of f, I'm going to get 2x plus 2y, 2x. And that brings me right back to the field I started with. P is that part. Q is that part. That last step is just to check my work, or rather to show again that this function f is a potential function that generates the field that we were interested in. And by taking its gradient, I saw that I came back to the same thing. Hi. Oh, yeah. I see what happened there. Yeah, that should have been 2xy, not. Yep, good catch. It was one where I think I already knew what the answer was, so I stopped paying attention to my work. Yeah, definitely should have been 2xy, not x squared. Which makes a lot more sense because I should see mixed terms showing up in both integrals. But I definitely don't want to see a term that depends only on x show up in the y integral. There's no way for that to happen. Yeah, either way, didn't change the next step. X squared plus 2xy. And now that I've done all of that, I can say that the fundamental theorem, which says that if I integrate from a to b of grad f dot dr, that is f of b minus f of a. I'm using a little bit of shorthand there, but it's roughly that, right? Because that is the fundamental theorem. If I take an integral, it's just from a to b, it's f of b minus f of a. So I just need to plug my 2 points in, which were -3, 0 is where, or 0, -3 is where we ended, and 3, 0 is where we started. So if I think back up to the top, this is my B and that's my A. So I need to plug in 0, -3 first, and then subtract plugging in 3, 0. So if I plug in 0, -3, I will get 0 plus 0 minus, if I plug in 3, 0, I'll get 9 plus 0. So in the end, I get 9. -9. I'm not very good with numbers this morning. Yeah, 0 minus. Hearing a fair amount of murmuring, which usually means I've made an arithmetic mistake. So if you think you see one, let me know. You go 3 for 3 on this first problem. Hi. Aha! Did I plug in 3 pi over 2? No, I didn't. Because I ended up finding that my integral was path independent because it's a conservative field, meaning that the specific traveling along that arc wasn't necessary. I could just go straight from point to point. Yes. Where did I plug in 0, -3? I started plugging stuff in to this function. Right, plugging it into f itself. Yeah, it's kind of like that. If I draw some arrows to highlight what I was doing. Alternatively, you could also calculate that integral directly. I chose not to go that route, but that's what all these hints provided were for. Is that if you do parameterize based on the curve I gave at the beginning and did the actual line integral along the path, you can use, well, you'll end up seeing you get these three terms that show up in the integrand. You'll have a sine squared term, you'll have a cosine squared term, and you'll have a sine times cosine term. And then you can just plug all that in and see what you get. Should hopefully come out to 9. Hi.
Can you explain when you got the
Yes. So R of t, start there, that's one. I'm parameterizing a circle, so just go to polar coordinates. R cosine theta, R sine theta. My radius is 3, hence 3 cosine theta. Then I need the bounds on theta, which means looking at the 2 points I'm at. And just think about the unit circle. Instead of 1, 0, I've got 3, 0. Instead of 0, -1, I've got 0, -3, just because that's what R is. But yeah, just thinking about the unit circle got me there. Right. The f function near the end there, yeah. So this f function is a union of what color have I not used it? How about green for the two parts to come together? Yeah, that f function is a union of the two integrals that I took of my field components p and q. Basically, I just needed to integrate the two things, take all of the unique terms, and just put them in a function together. It's not exactly adding them together because I do not want to have 4xy. I just want 2xy. But yeah, if I has another term in there, like maybe I could have had a minus y cubed or something. There could be another term that depends only on y, and I would have want to put that in the function as well if I had one. Yeah, this example just didn't have one. All right. Well, let's try another one. All right. One of the easier questions. Finding the gradient of the function provided. It's a 3-dimensional gradient, so we'll have all 3 components. But that's fine. I just need to take each partial derivative one at a time. So grad f is the vector function. Let's see. If I take an x derivative, I'm going to get 0 plus 7z. Since there's no x in that first term. If I do a y derivative, I think I'll get 15z e to the 5y. I'll have 3z e to the 5y times 5 because I need to multiply by the derivative of 5y plus 0 because there's no y in the second term. And for the z component, take a z partial. I'm looking at 3 e to the 5y plus 7z. Nope, plus 7x. And each of those two terms has a linear z component to them. So just take the derivative of z and you get 1. And that's it for that problem. So hopefully that one's again tomorrow. So I'll assume that that one went fine, and let's move on to a parametric representation of the part of the sphere, that thing that lies above the cone, that other one. Don't forget to include bounds for both parameters. So this is a cylindrical and spherical coordinate problem in disguise. Is the hint I'll start off by saying. I want to parameterize a sphere. Let me just highlight a couple of pieces here. Parametric representation of the sphere, which makes me think I'm going to want spherical coordinates. Spherical coordinates. I'll abbreviate that so that I don't accidentally misspell coordinates live in front of everybody, because I'm sure I would do that. So we can go to the formula sheet to find our spherical coordinates, but they are x equals rho sine phi cosine theta. X is rho sine phi sine theta, and z is rho cosine phi. And since I've got the two different angles in there, I'm going to highlight which one's which to make it a little easier to parse where the different angles are going. So I want to adapt my spherical coordinates into this parameterization. I'm parameterizing only the edge of the sphere, right? It's not a solid, it's just the surface. So I'm only going to need two parameters. In fact, I'm only allowed two parameters by the time I'm all done. Fortunately, there's a pretty easy replacement for rho, the three-dimensional radius, because I know that the sphere in question has a radius of 4. Right, that 16 should be rho squared. Meaning rho itself is 4. So I'm just going to come through and change each of those to be 4. Then you could stop right here and claim this is a valid parameterization, and we would definitely take it. If you want to parameterize in terms of phi and theta, those are valid parameters. So you can just write those in and be done. If you're particularly attached to the way that WebWork does stuff, it will often rename things to S and T instead. Where S will be my blue one and T will be my green one. We usually replace theta with T because T and theta just kind of tie together really nicely. Right? They're both kind of a T. Theta starts with T. And then S is next to T in the alphabet, so it gets to be the other one. But if I were to write this thing out as a vector function, it would look something like this. For sine S cosine T, for sine S sine T, for cosine T. I already see I've made a mistake. So I'm go fix that. I had it right when I wrote it down the first time. Z should depend only on the phi parameter, not theta. Theta only shows up in X and Y. So Z is for cosine S. Cool. I think you could leave your parameterization either way and you take it. You can leave it in terms of its three component functions, one for x, one for y, one for z, or you could write it out as a full vector function. Full parameterization R of two parameters equals the thing. Either way is going to be fine by us. We'll know what they mean. So whatever feels comfortable to you. Hi there. Can you say that a little louder? Yes, we do need domain space. Yep, and yeah, I haven't come to that part just yet. But yeah, we are going to want to throw in bounds for S&P. Hi. Oh, yeah, you can use whatever parameters you want, right? Just define them and use them and it's fine. So yeah, S and T are standard, but so are U and V. You see those a lot. Phi and theta are nice because they make more sense to us. If you wanted, I don't know, draw a picture of a tree and a squirrel and use that as your two parameters. It would take a lot more time, but you could do it. Yeah, use phi and theta, S and T, U and V, whatever two you want will be fine by us. U and V are a little tricky because they tend to look like each other. This is why I like S and T better, but yeah, it won't matter. As long as your handwriting's neat, it'll be fine. But right, we should come up with bounds for S and T as a broad guess. S is in 0 to pi. Theta is in 0 to 2 pi. Start there. And then pare it down as you need to. If these were my two bounds, I would parameterize the entire sphere. But since I'm only going to parameterize part of it, I know I'm going to need to make an addition here. Hi.
Bounds for 5
They will be something different. Yes. Yeah. So this is just our starting guess. We're going to find out in a minute that this one's wrong. But the other three, I think, are correct. So let's go figure out why that's wrong and what we should have there instead. But it's at least a first good guess. Because again, if I went with those bounds, I would parameterize the entire sphere. But I want only the part that is above the cone z equals root 3x squared plus 3y squared. So since I'm only looking above that part, that's going to change what my phi angle should be. But I'm still going all the way around the z-axis. I'm going all the way around the xy plane. So 0 to 2 pi still works for theta. So I like my theta bounds. I just need to fix the I just need to fix the theta boundary. So I'm going to need to use that cone to figure out what bound it's talking about. A couple of ways I can do that. I can just find the intersection between the sphere and the cone. I have an equation for z. I can plug it in for z up there, solve that equation, and I should hopefully get something out on the other end. I can also just solve the equation of the cone for the angle that it is. Because we know in spherical coordinates, or hopefully one of the things we remember from spherical coordinates, is that cones have the equation phi equals c, where c is some constant value. Right? In spherical coordinates, we can express a cone with this rather simple equation. So if I figure out what that angle is, I ought to be all set. So I'm going to do that. So with some of the space still available to me, let's go with z equals the square root of 3x squared plus 3y squared, which is going to be the same as the square root of 3 times r, where r is the cylindrical coordinate. but I'm going to use that sort of half measure step because I think it's a little easier to solve from here to say that z, which should be rho cosine phi, is equal to the square root of 3 times rho sine phi. And then start trying to solve this equation for phi. So r from cylindrical coordinates I know is equal to rho sine phi. So if I do that, I'm going to start putting things all on different sides. I'm going to have a 1 over square root of 3 on the left side. So I'm going to divide my square root of 3 over there. On the right side, rho sine phi divided by rho cosine phi. The reason I wanted to arrange my trig functions this way is that I know sine over cosine is tangent. So I've got that tangent of phi is equal to 1 over the square root of 3. Or maybe I want to rewrite that to be square root 3 over 3. It's fine. In the end, I'll hopefully recognize this as pi over 6 is fine. Though if you forget some of your tangent values, and you just leave this thing as arctangent of 1 over the square root of 3, that'll be fine as well. But again, hopefully, the problem's a little easier if you remember your unit circle. So instead of pi for that second S boundary, I wanted pi over 6. But with that, I have a full parameterization. All the way down to it right there. Hey there. Aha! So since the original question was like x squared, y squared, and z squared, how come we're not squaring things inside this vector field, right? Or inside this vector function? It's for the same reason that we don't square the components inside the vector function when we're in polar coordinates. Right, a circle is x squared plus y squared equals r squared. But then the two equations are x equals r cosine theta and y equals r sine theta. When I take these vector functions and plug them back into the scalar function I started with, x squared plus y squared plus z squared, that whole expression will simplify to 16 because I'll use two separate Pythagorean identities. The idea that sine squared plus cosine squared is 1. If I do that twice, I can condense that all the way back down to 16. So it's when I plug them back into the original equation, that's when they get squared, and that's when it all simplifies back down. But in this step of it, in the vector equation step of it, they're not squared. And again, you can just find that off your formula. Hey there. When is t not equal to 0 to 2 pi? Let me move that over here. Let me scroll over here, you jerk. Okay. Because this is actually a pretty solid question, I think. When is theta not 0 to 2 pi? So when is it not that? If I said something like, how How about x squared plus y squared plus z squared equals 16? We'll keep that part the same. And y is greater than or equal to 0. But if I gave you something like that, then theta is in 0 to pi. If I said the same thing, but x greater than or equal to 0, now theta is in negative pi over 2 to positive pi over 2. All right, so if I start putting restrictions on x and y, then we'll see that happen. As one last aside, if I gave you z was greater than or equal to 0, that now means phi is 0 to pi over 2. I'll highlight that one second. Yeah, so again, it's really just about restrictions on x and y are what will change theta. Oh, but all right, let's move on to a max and min problem. Yeehaw. All right. Can I finish this problem before class ends? I can if I take some shortcuts. But okay, find an absolute maximum and minimum of the function f on the set of points that are the semicircular disk that encompass everything that is on and inside a circle with a radius of 5, and y is less than or equal to 0. So it might be helpful to sketch the region in question. So here's going to be our circle. And somewhere over here, zoom, I need you out of the way. I can draw some coordinate axes in. Ugh, what has happened here? All right, good enough. Except I can't leave well enough alone. That circle's so off center. Good enough. Okay, so there's our circle. It's going to have a radius of 5. R equals 5. I need to be less than 0 for y. So I'm looking at just that region down there. That's my domain. All right, let's start trying to find critical points. So the first step is usually the easiest step, just finding your critical points that are on interior. There. I am going to want to look at f partial x and f partial y. I'm going to set them both equal to 0. Right? Critical points are always about taking a derivative and setting them equal to 0. So I'm going to want to do that every single time. So partial x, I only get 2x. Everything else has a partial derivative of 0. That's equal to 0, so x is equal to 0. Cool, easy enough. On the other side, finding f partial y, well, I'm going to get 8y plus 24. And I also need that equal to 0, which gives me a solution of y equals -3. I have a system of 2 equations. It's a very simple system. just x equals 0 and y equals -3. That has only one solution, 0, -3. I think red will highlight on here pretty well. Yeah. So I've got a critical point right there. All right, that's step one. I have a single critical point on the interior. Move it down just a little bit. So the rest of the problem is about finding critical points on the boundary. So that's going to be fun. And I have two different boundaries. Yeah. Right, one of those boundaries is this purple line that I drew in. It's at y equals 0. And then the other boundary is going to be the circle. More on that in a minute. Let's do the easier boundary first. So boundary curve number 1. Let me start labeling some things. We'll call this the interior. And then we'll go look at the boundary. So, and the boundary, again, will be made up of two curves. One of those is just f of x 0. Because I'm just going to plug in 0 for y, because that's the upper boundary curve, which just gives me the function x squared plus 0 plus 0 plus 2. So its derivative is very nice. F prime of x is just 2x, which needs to be equal to 0. That'll give me the point 0, 0. I can see from my derivative that x is 0. If 2x is 0, means x is 0. And then just go back to the boundary equation, which was y equals 0 to find my y value. So I get, again, 0, 0. Oh, did we? No, we didn't die yet. Come on. Come on. Color that in purple. So I wasn't very clean with my boundary curves after I brought that point in next debate. But cool. 0, 0 is a critical point. Now I've got, now there are two of them. Let's go find even some more. Along the circle, which is going to be my other boundary curve. So f of something. I need to go parameterize that curve. And also, one thing that I kind of didn't mention yet, but I should have back when I was putting this boundary curve together, I needed endpoints. I needed a domain for that purple curve, right? If I'm coming up with a parameterization, it needs to have its bounds on it. X here is between -5 and 5. That part will be important in a second. Cool. Coming back to this circle. If I'm doing things the most proper way, I'll find some r of t. And I'll probably say that it's 5 cosine t, 5 sine t. T is in between 0 and 2. Nope. Try again. T is in between pi and 2 pi. since I'm trying to take the bottom half of the circle, that would be my polar parameterization for that curve. That will work. You can solve it that way. I'm gonna suggest maybe a slightly better option. If I look at my function, it only has x squared in it and no other x value. So if I could just replace x squared with some expression, I could have an equation for my boundary that contains only one variable, only one parameter. So while we normally wouldn't want to define x as plus or minus the square root of something, if I can just define x squared and not worry about x itself, I can come up with a rather nice parameterization for that boundary curve. Namely, that on f, I'm going to say that x squared is equal to 25 minus y squared. Letting me say that f of just y leaving me to just say I can replace that one term in our function. There we go. With 25 minus y squared plus 4y squared plus 24y plus 2. And this time I need to say that y is in between -5 and 0. Yep. So this is now f of y. And I want to find a derivative of this thing, f prime of y is something. It looks like -2y plus 8y plus 24 equals 0. So I'll have 6y is equal to -24, meaning that y is -4. Now, if y is 24, that means x squared is 25 minus 16, which is 9. So x is plus or minus 3. So I end up with 2 more points. 2 more critical points. Oop, I dropped the negative, didn't I? Plus or minus 3, -4. So I'll come back up to my picture and I'll place these 2 critical points. Finally, in addition to these 4 points, I have 3 more. Here and here and here. All of those are my boundary points, right? They're the end points of my parameterizations. The top 2, I can get those just off of the purple line. X has to be between -5 and 5. So I've got 5, 0, and I've got -5, 0. Because my y parameter, my parameterized the lower half of that curve, I knew that y could only be between -5 and 0. I'll come up with 3 boundary points on that curve. One of those is at 0, -5, because I need y to be -5, which forces x to be 0. That's the one at the bottom. 0, -5. And then And then if I plug in 0 for y, I'll get plus or minus 5 for x. I come up with the same two boundary points that the purple curve had. They line up with those two on the left and right sides. So in the end, I just have to plug all of those in and see which one is biggest and smallest. So f of, I'll have 0, -3. I'll have to do f of 0, 0. I'll have to do f of plus or minus 5, 0. I'll have to do f of 0, -5. I'll have to do f of plus or minus 3, -4. And that's all of them. So you'll plug them all in, and whichever one's the biggest is the maximum, and whichever one's the smallest is the minimum. I'm pretty sure you'll find that this one is the minimum, while this one is the maximum. But I'll leave that as an exercise because I know that I am out of time. All right, there were 2 problems that I didn't get to. Number 6, we did this one yesterday in class, so I'll leave that one alone. The only one we didn't really talk about then is a tangent plane. We kind of talked about that yesterday too, but if you look at my notes after class, I'll have filled in the work for this problem. Hi.
For 6, if
Yeah.
number 6, a question like that is on the exam, if you leave it in and key, ask it for partial S.
Yeah, so you will need both.
But just like when we're needed to have it only in some
The web work needed it not in terms of X and Y. Right, that's the key step, getting rid of X and Y. And then S and T are at the same level, so they have. That said, though, we probably won't be too big.
And that's why, but
But since I've still got this class maybe for a minute, I might just do this problem right now.
There be like vector field graphs, like they can show up.
They could show up.
They could, they won't.
Okay, good.
Okay, that's good. Thank you.
Is there gonna be like vector field, like other questions or like to not with the graphs?
I think that the only way that we bring up vector fields on the exam is within the context of the line.
Like
Okay.
one.
Yeah, like question number
Okay.
one. Yeah, if you do question 1, I think you're all set. I did add one other problem that I think is worth looking at. I didn't have time for it. I'll also fill this one out. We never did a scalar line
Okay.
in class. So that's the one problem outside of the practice exam that I'm.
Okay.
And I'll also add it here.
Like, can you go back to number 1?
Yes.
When I did it, I like did it in the way with these.
Yes.
So if I like was practicing it, that I like had like AI generate me a bunch of example problems.
Mhm.
So like, is that fine if I do it that way? Because that's the way I practice.
Yes,
Okay.
that's because I mean you should have hopefully still gotten -9.
I did, yeah.
Right, perfect.
So okay,
Yeah,
it
if you
doesn't
got
matter.
-9, we're not going to care too much about the method.
Okay.
The only thing that could get you trip up is if we specifically ask, show that this field is conservative.
Right.
You got to make sure that
You
you
can
can
do
do
that.
this.
Okay.
But if you show it's conservative and then go back to integrating it the standard way,
That's fine. Okay. Perfect.
Perfect.
Thank you.
You're welcome.
I saw this like right after.
I do.
Is that in res?
My office is that way.
Okay.
Yeah, so go over to the C wing of Wells Hall. Yeah, C wing. I'm up on the 5th floor.
Okay.
Cool. I'll see you there in a minute. Hey, what's up?
So, because there was a lot of max or critical points on that problem
Mhm.
during the exam, like if I'm running out of time and because I can assume that like 0, -5, or like, the
Mhm.
outer edges, what would be like the penalty on that, even if it is correct? Like
Oh, you mean like if you test extra points?
let's say I just assume that like
Ooh.
-5,
Yeah,
0 is a critical point, right? Like, would I still get some points for that, or is it
Yes.
okay?
You'll get penalized if you miss a critical,
If I miss
but you
one.
won't get penalized if you add extra points. If that
Okay,
makes sense.
I guess
Yeah.
that would.
Yeah, because yeah, you could, yeah, looking
Could
at
I-
that circle
I don't know.
problem, you can probably say, just, because if you're working fast, you're trying to save time, I'm just gonna check the top and the bottom, the left and the right, just throw them in there, because like maybe that's the one, right? Yeah, you're not gonna get penalized for checking.
But if I don't write one down that exists, then it'll be points on.
Right, yeah, you'd be in trouble there, right? Because like I think an easy one, like if you miss the plus or minus 3, -4, like that one's important. You lose points if you didn't find this one, which comes from the derivative on that circle. Right, if that gets missed, you'd be in trouble. But if you like, say you didn't show the bounds for X and for Y here, you just said, I'm gonna pick all the points on the circle, right? Like this one, and this one, just because they're the furthest left and right, they're the furthest top and bottom, X and Y are my variables. So probably
Should I be
Yeah.
expecting to have this many
This
critical
many?
points though? Because this is
this is a lot.
Yeah.
In fact, I thought there were fewer than this when I went to this exam.
okay.
And then I was like, oh, yeah, crap. That's
And
more than we
The
wanted.
two types of line integrals are important to know. Like I got
Yes.
into them both.
Yep, we only had time to go over one in class. But I'm still recording, aren't I? Hi, everybody watching online. I am gonna do this problem, which is gonna be a scalar version of the integral, of a line integral.
Okay, thank you.
And then, yeah, just look at that. And, yeah. Sweet. Okay. So then real quick, finding the equation of a tangent plane. Let's do this. F is the function z plus 3y e to the x y equals 0. That part's important because then I can go take grad f and have something which looks like 3y squared e to the xy, 3 e to the xy plus 3xy e to the xy, 1. And then I can go look at grad f of my point, 0 to -6. And it is something nice, I hope. Let's see, 3 times 4 is 12. And e to the 0 is 1. Then I'll get 3 times 1 plus 0, and then 1. Let's just double check that all looks right. Leave it does. All my x's are 0s. So that wipes out that second term. Now that I've got my gradient, I can use that to construct a tangent. Rather, I can use that to I can use that to construct a tangent plane to say that this thing is 12 times x minus 0 plus 3. It's actually not that way. Do it all in, I think, red, what I like best. 12 plus 3 times y minus 2 plus 1 times z plus 6 equals 0. And that's a tangent plane. Because I know that this gradient is my normal vector. I think that's the easiest way to come up with a tangent plane. You can also use the linearization formula that's given on the formula sheet. And then, well, I've still got a little bit of time. We didn't actually look at a scalar line integral. I'm going to do one of those here. So the density of my wire is the square of its distance from the origin. So I am looking at integrating d squared, where d is distance from the origin, d squared ds over my curve, which is going to look like the integral of x squared plus y squared plus z squared, the square root of that squared. So that's my square of the distance from the origin. All of this times ds, which from the formula sheet, we know this is the magnitude of r prime dt. So I'm going to need to know r prime and plug that stuff in. I also am just sort of given my bounds for t. They're 0 and pi. So I need r prime. I suppose first I'll just write down what r is. It's already given to me, but I'll be explicit about it. It's 2t, 4 cosine t, 4 sine t, which means that r prime is 2 negative 4 sine of t, 4 cosine of t. So my magnitude of r prime of t is the square root of 4 plus 16 sine squared plus 16 cosine squared, which is going to simplify to square root 20. Sine squared plus cosine squared is 1, which means I'll have 4 plus 16, which gets me to 20. So I then need to integrate from 0 to pi. R prime is the square root of 20. I'm just going to pull it out in front. I need to plug in everything else, x squared plus y squared plus z squared. So this will be 4t squared plus 16 cosine squared of t plus 16 sine squared of t dt. And then that integrates somewhat nicely to the square root of 20 times 4/3 pi cubed plus 16 times pi plus 16 times pi. And then you can simplify that if you want to. But anyway, that's how I would solve this problem, in particular paying attention to the method we used at the beginning. If I want to integrate a scalar function, which I knew I had a scalar function because f is this bit right here. That's f. It's a scalar function as opposed to a vector function. So I'm going to use the scalar line integral method. Again, that one's on the formula sheet, but it means you've got to find the magnitude of r prime. We do not need to check for a conservative vector field when we're integrating a scalar function because we don't have a vector field with which to check. So we'll just calculate it the direct line integral way. Okay, and with that, I'm done. Am I done? There's one other problem. I'll fill in some detail here later. But this is pretty similar to the first problem that we did. This is integrating another vector function. It just requires noticing over here that f dot dr is pq dot dx dy, which is p dx plus q dy. So I can separate out my two components, p and q. They are 6x squared and 2y squared. Again, we did a problem similar to this on Monday's lecture. So check that if you want to see more detail. Okay, and now for reals, I'm out of here. Okay, bye, 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 bye.